Hi everyone, this is Hussein from EJ Academy. In this video, I wanted to go over an integration problem from calculus. This problem is related to one of the applications of integral. And let me read the problem for you. So we have a cone frosting, and we wanted to fill it with water using a pump. And the question is asking to calculate the amount of work to pump the water all the way to the top. So we're going to fill this cone with water from the bottom. And then as it gets filled, the level of the water comes up until it reaches to the top of the frosting. So the height is 10 feet. The radius at the bottom is 4 feet and at the top is 8 feet. So let's go ahead and solve the problem. So there is a little bit of geometry involved. If I, let me assume a thin layer of water at some arbitrary height. Let's assume this is a thin layer of water here. Let me draw that again. Okay, now it's better. So at this point, this is at the, let me see, this is at the height of y from the top. And then at this level, let's assume the radius is small r. The radius is r, and I wanted to find the relationship between the radius and the height. So I know that at the very top, which y is 0, when y is 0, the radius is 8 feet. And at the very bottom, when the y is 10, then the radius is 4 feet. So basically, this radius is a function of r. I'm sorry, radius r is a function of y. So to find that, we can, let me draw a diagram for you. Okay, I'm going to use this shape to draw the diagram. So I'm going to assume, I'm going to draw a vertical line connecting all the centroid of these circles. And I'm going to extend this line. And then I'm going to also extend this tangent line here. So these two lines are going to intersect at point O. And I don't know at this point, I don't know, the distance from O to, let's call this point O1. I don't know what is the distance between O and O1, but I'm going to assume this distance is A. So I'm going to use the relationship between similar triangles to basically calculate A. So the ratio of 8 to this height here, which is 10 plus A, so 8 over 10 plus A is equal to the ratio of 4 to this distance A. So 4 divided by A. So if I simplify this, I'm going to get 8 times A is equal to 4 times 10 plus A. Then 8A is equal to 40 plus 4A. And then if I solve this for let me do this. So 8A, I'm going to move this 4A on this side to the other side. I'm going to change the sign. So it's going to be negative 4A is equal to 40. Then 4A is equal to 40. And as a result, A is equal to 40 divided by 4, which is equal to 10. So this A is equal to 10. Now, I'm going to write another relationship between similar triangles, but this time I'm going to assume that I have this small triangle here and also this triangle with the base of R. And my goal is to find the relationship between R and Y. So the ratio of 4 to A, 4 divided by A, which is equal to 10, is going to be equal to the ratio of R to this distance. So this distance is equal to 10 plus A minus Y, which is equal to 20 minus 1. So the ratio becomes R divided by 20 minus Y. And then I'm going to simplify that. So I have 4 times 20 minus Y is equal to 10 times R. And remember, my goal is to find R. So I'm going to first simplify the left-hand side. So 4 times 20 is 80. 4 times Y is 4Y is equal to 10 R. And I'm going to divide both sides by 10. So I'm going to get 80 minus 4Y divided by 10 is equal to R. Then R is equal to 80 divided by 10 is 8. 4Y divided by 10 is 0.4Y. So I have R is equal to 8 minus 0.4Y. So this is the relationship between R and Y. Now that I have out of the way, I can focus on calculating the work of the pump. Okay, let me copy. Actually, let me copy this figure here with all the dimensions. I'm going to copy that. I'm going to move to a new page. I'm going to paste it here. Okay. I don't need the problem. I don't think I can delete that. Anyway, so let me see. I wanted to calculate the work. So I'm going to show the work done by the pump to basically, so let me see. I have this, let me highlight that. So I have this disk of water. And then this disk of water is going to be pushed up by the pump. So when we pump, this disk of water is going to be pushed up until it reaches to the top. So we wanted to calculate the work that is done by basically moving this volume of water from this location here to the top of the cone. So let me first calculate the volume of this water. So the volume of this water is going to be, I'm going to call that dV because this is such a small volume of the whole water. So I'm going to call that dV, and then dV is the area, which is pi r squared times the thickness. So I'm going to call the thickness of this disk dy. So dV is the area times dy. So basically this pi times r squared is the area, and then dy is the thickness. Okay, now, so I'm going to leave r as it is. I know what's the relationship between r and y. So I have it up here, but I'm not going to replace it now. I'm going to do it at the end. So next step is to find the mass of the water. So I'm going to call that, use screen. So I'm going to call the mass dm because this is, again, it's a fraction of the whole water mass. So I'm going to call that dm, which is the density of the water. Let me call that rho. So rho is the density of the water multiplied by dV. So this is the density of the water. So the density of the water is, because we are using US units, the density of the water is 62.4 pound per cubic foot. And then, so if we substitute dV with the equation that we found up here, so it's going to be rho times pi r squared dV. I'm sorry, dy. And then the next step is is to find the force. We know that there is a gravitational force applied to this mass. So I'm going to call the force dF, because again, this is a fraction of the force applied to the whole mass of water. So this dm is going to be equal to the gravitational constant g times dm. And this g, again, because we're using US units, this g is, if I'm not mistaken, 32.17. 32.17. I think the unit should be, let me see, I have a table right here. So the unit for G is, I think it's a gravitational acceleration, right? So it's foot per second squared. So this is gravitational acceleration. So I'm going to replace dm with the relationship I have up here. So I have g times rho times pi r squared times dy. And then, so finally, I'm going to calculate the work. So the work is defined by force times the distance that force applied. So we apply the force. This force dF is applied here, and then the distance that this force is going to be applied by the pump is from here all the way to the top, which is y. So this dW is force times the distance. So I'm going to replace dF by the relationship I have on the line above. So I'm going to have g times rho times pi times r squared times dy times y. And then I'm going to just rearrange all this these parameters. So I'm going to have pi times g rho r squared. Let me write y r squared dy. And then now it's the time to replace r with the value that we found up here with this equation. 8 minus 0.4 times y. So I have pi g rho y times 8 minus 0.4y squared dy. Okay. Now, this is only the work done by the pump to move this fraction, this volume of the water to the top. Now we need to integrate it or add all the work done by the pump for like other volumes of water. So we use integration. So W is the total work. So this is the total work done by the pump. So that total work is equal to the integral of dW. So basically, we're summing up all the small work done by the pump. And then this is going to be a determinate integral. So let me replace dW by the relationship I found up there. So pi times g rho y times 8 minus 0.4 times y squared dy. As you can see, the variable in this integral is y, and the lower and upper limit of the integral is the lower and upper limit of the y. So we start pumping from the bottom all the way to the top. So y changes from 0 to 10. So I'm going to do this integral from 0 to 10. And then these are all constants. So I'm going to take them out. So I'm going to have pi times g times rho integral from 0 to 10 y times 8 minus 0.4 y squared dy. And then to do this integral, I need to just expand that term inside the integral. So I have pi g rho integral from 0 to 10. So I have y times, so the expression inside the parentheses, if I expand it, I'm going to have 64 minus 0.4y times 0.4y is 0.16 y squared minus, let me use my calculator. So 2 times 8 times 0.4 is 6.4 y dy, and then I'm going to rewrite that integral. This time I'm going to multiply y with this parenthesis, so I'm going to have 64y minus 0.16y cubed minus 6.4 y squared dy. Now, doing this integral is easy because these are, I have three, this is a polynomial, so it's going to be easy to do this integral. So I'm going to have pi g rho. So the integral of the first term, 64y, is 64 times y squared divided by 2. And then the second integral, the multiplier is 0.16. So y cubed, the integral is going to be y to the fourth divided by 4. And then last term is going to be 6.4 y cubed divided by 3. And then the lower and upper limit of the integral is from 0 to 10. So let me very quick do the math using my calculator. So I have pi times g, which is 32.17, times rho, which is 62.4, times 64 times y squared is 10 squared, which is 100 divided by 2, minus 0.16 times 10 to the fourth divided by 4, minus 6.4 times 10 cubed divided by 3. All right. So the answer is 9.25 times 10 to the power of 6. And the unit for the work in US unit is, because it is force times the distance, so the unit is going to be, let me see. So the unit is going to be pound foot. Okay, the unit for the force is pound. The unit for the distance is foot. So I'm going to have pound force. This is not a pound mass, this is pound force multiplied by foot. Okay, so let me very quick, I wanted to show you how you can solve this integral with Python. So this is a really cool, so let me switch to Python. This is a collab with Google. I'm going to insert a new cell. I'm going to import a couple of library. So one of the library I need here is the math library. I'm going to import that as M. And then another library that I need is SymPy library. So SymPy is a library that allows me to do symbolic math and also do integration. So I'm going to import that as SP. All right. So these are the two library I'm going to use. Then, so I'm going to define my function. So the keyword is def, and then the function I'm going to have is, so the variable here is y. So first I wanted to define my constant. So I'm going to define the gravitational constant 32.17. Then I'm going to define water density 62.4. Then I'm going to return the value of the function, which is pi. So pi is a part of math library, so I imported math as m. So I'm going to say m dot pi. So that allows me to access to the value of the constant pi, then multiplied by g, then multiplied by rho, then multiplied by y, and multiplied by r squared, which was 8 minus 0.4 times y, and then the whole term inside the parentheses is r. I need to make it a squared. So to do a square in Python, you use double asterisk and 2. So this is my function. So far I imported 2 libraries. I defined my function. Now I need to use a SymPy library to make y, basically to convert y to a parameter instead of a variable. So I'm going to let me scroll this up. Okay, so I'm going to say y is equal to, so to access SymPy library, I imported as sp. Then I use dot notation, and so I'm going to use a function called symbol. So the function symbol basically converts, it just tells the code, the program that I wanted to consider y as a symbol. Okay, now this one is taken care of. I can calculate my integral. So I'm going to directly print the result. So I'm going to use print function, and inside the print function, I'm going to do the integration. Integral is part of a SymPy library. So I'm going to use sp again dot integral integrate. Yeah, these are the options. So I'm going to use integrate, and then inside the parentheses, I'm going to specify the function name, which was f y, and then comma, and then another pair of parentheses. Inside, I'm going to specify the variable, which is y, and then the lower limit 0, and then the upper limit 10. Let me see if I have enough close parentheses. So I have 1, 2, and 3 open and 3 closed. Okay, sounds good. Let me run this. Okay, there we go. So the answer is 9249472, which is almost 9.25 times 10 to the power of 6, which is the same answer that we found in your notebook. All right, that was it for today. I hope you learned something in calculus. So in this problem, we reviewed one of the problems related to application of integral in physics or mechanics, and also I try to show you how you can use Python to solve this integral. So if you have any questions, like always, you can leave your question in the comment section below this video. If this video helped you, I appreciate if you hit the like button. Also, don't forget to subscribe to our channel to get notified for future videos. Till next video, bye everyone.